Okay, so to start, vectors, the graphical representation of a vector looks kind of like a ray in geometry, the rays that you used in geometry, but the main difference is that in geometry, a ray goes forever. Its length, you can't measure the length of a ray because a ray goes forever. But vectors, we use a geometrical representation. The length of the vector actually does mean something. The length of the vector it could represent a force, a velocity, an acceleration, lots of different things. So for example, I could say this is a 20 Newton force pointing in that direction. Okay, so the important thing to understand with vectors is that it's the magnitude, which really means the length, and the direction that matter. The position of a vector doesn't matter. So if I have a 20 Newton force pointing at a direction of, let's say, 30 degrees above the horizon, if I move that to another location, it's still the same vector. Okay? So vectors don't really have a position, they just have a length and a direction. And that's all that's important. Writing vectors in component form, if you think of a vector on a coordinate system, if I had a vector that started at the origin and ended at the point 4, 2, then we would just simply call that vector, if this is vector u, then I could say vector u is the vector in component form 4, 2. So we can write the x component and y component of a vector. Now that doesn't mean that it has to start at the origin. That just means wherever it starts, it's going to go 4 units in the x direction and 2 units in the y direction. So for example, I could start the vector down here at the point 2, negative 3, and vector u goes 4 units in the x direction and 2 units in the y direction. And so there is another copy of vector u. Again, its position doesn't matter. It doesn't have to start at the origin, but when we write the component form 4, 2, that means it starts at wherever it starts, it's going to move 4 units in the x direction, and it's going to move 2 units in the y direction. Okay, and the advantage of writing vectors in component form, we'll see a little bit later, it's a lot easier to do a lot of the algebra and calculus that we need to do with vectors, for example, adding them, subtracting them. We won't do dot products and cross products in this class, but everything that you do with vectors is a lot easier to do in component form typically. Okay, the magnitude of a vector is just its length. So this vector u that we're looking at, to find out how long that vector is, if we're going 4 units in the x direction and 2 units in the y direction, we've created a right triangle, so we can just use the Pythagorean theorem to find the magnitude. And we use vertical bars that look just like absolute value bars to denote the magnitude of a vector. So the magnitude of u would just be the square root of 4 squared plus 2 squared using the Pythagorean theorem. So that would be the square root of 16 plus 4 square root of 20, or 2 root 5. Okay, so magnitude is a scalar number. It represents the length of the vector, or the magnitude. If this was a force, like I said earlier, if it was a force of in newtons, then this would be 2 root 5 newtons. Okay, so in general, to find the magnitude of a vector u, if we have a vector that in component form is a comma b, then the magnitude of that vector is the square root of a squared plus b squared. Okay, to find the direction angle, that's the angle with respect to the positive x-axis or with respect to the horizon. The direction angle, we can use inverse trig. So for example, looking at this vector that we drew up above, 4 in the x direction, 2 in the y direction, to find theta, I could say theta is equal to inverse tangent of opposite over adjacent. If I work that out on the calculator, inverse tangent of 2 over 4 is 26.565 degrees, or if you had it in radian mode, that is about 0.4636 radians. Okay, in general, the direction angle is inverse tangent of the y value over the x value. So b over a, if we have a vector if u is equal to a comma b again, then its angle is the inverse tangent of b over a. Now that's if the vector's in quadrant 1 or 4. Because remember, the inverse tangent function will only give you answers that are in between negative 90 degrees and positive 90 degrees. So if we know that our vector is pointing into quadrant 2 or 3, what do? Does anyone remember? Say that again? Add 180, that's right. And so you need to make a note to yourself to add 100 degrees if u is in quadrant 2 or quadrant 3. Okay, so you have to look at the coordinates of your vectors. If either the x-coordinate or the y-coordinate is negative, then you know you're in quadrant 2 or 3, and you add 180, because the inverse tangent function will only give you answers in quadrants 1 and 4. Add 180 to get into quadrants 2 or 3. Okay, so go ahead and try example 1. Find the magnitude and the direction angle for the vectors 2, 6 and negative 5, 5. Okay, the magnitude of vector 2, 6 is going to be the square root of 4 plus 36, so the square root of 40, or 2 root 10. And the angle is the inverse tangent of 6 over 2. Which is about 1.249 radians, or 71.6 degrees. And then for example B, the magnitude is going to be the square root of 25 plus 25, square root of 50, or 5 root 2. And the angle, when you do inverse tangent of 5 over negative 5, it tells you it's negative 45 degrees. But we know that the vector negative 5, 5, if you plotted the point negative 5, 5, that's in quadrant 2. And so we know an angle of negative 45 degrees doesn't make sense. It's actually, we add 180 to that and get 135 degrees. Any questions? Okay. Vector addition, we can do graphically and algebraically. let's say I have a vector u that goes 2 units in the x direction, 1 unit in the y direction. So that's vector u. And then I have another vector v that goes negative 2 units in the x direction, 3 units in the y direction. I can add those graphically by making a copy of each one and connecting them head to tail. So here's vector u. And then vector v is going to go 2 units to the left. So I start at the end of vector u to start vector v. So I'm going to go 2 units to the left and 3 units up. There's vector v. So see, I connect them head to tail. And then my resultant is the vector that starts at the beginning of u and goes to the end of v. Okay, so that is called the resultant vector. That's what you get when you add two vectors together. And then we can do the same thing algebraically by writing the vectors in component form. If vector u, I'll use the same two vectors that I did graphically. The vector u would be 2, 1. The vector v would be negative 2, 3. When I add those, vector u plus vector v, I just add the x components. So 2, 1 added to negative 2, 3. Add the x components and you get 0. Add the y components and you get 4. So our resultant is the vector 0, 4, which would start at the origin and go up 4 units. So our resultant points straight up and has a length of 4. Okay, notice that that's the same vector that I got when I did them graphically. Scalar multiplication is when we multiply a vector by a scalar constant. So for example, if I had the vector, let's say vector u was negative 1, 7, 5 times vector u just gives us a vector that points in the same exact direction, but is 5 times as long. And in component form, all I have to do is multiply both the x and the y components by 5, so that becomes negative 5, 35. So again, that's a vector that is 5 times longer than the original vector and points in the same direction. Okay? Unless you multiply by a negative vector, like if I multiply by negative 2, then I get a vector that is twice as long and points in the opposite direction. So that would be positive 2, negative 14. So that's a vector that is twice as long and points in the opposite direction of vector u. Sure. Okay, go ahead and try example 2, A, B, and C. Okay, negative 4 times vector u would be negative 4 times the vector 3, 2, and so that is 12, negative 8. U plus v is going to be 1, 1. Add the x's, you get 1. Add the y's, you get 1. And the vector 2, u minus 3v, 2 times negative 3, 2, minus 3 times 4, negative 1. That's going to be negative 6, 4, plus negative 12, 3. So I changed it to vector addition by multiplying by negative 3, and so now it is negative 18, positive 7. Any questions? Okay. Okay, similar to what we saw earlier on in the year, just working with position functions and velocity functions. We can work with position, velocity, and acceleration vectors. So a position vector tells us the location of an object, and in our text and in many textbooks, they use the vector r for the position vector, and so we can break that into separate components, r sub x of t and r sub y of t. So that can be modeled on your graphing calculator in parametric mode because you have you have x and y defined independently. Okay, and then just as we did in the past, to get a velocity vector, or to get, when we're working with functions, to get from a position function to a velocity function, what did we do? We took the derivative. So the velocity vector, we just take the derivative of the position vector. So that's r prime of t, and so that is r sub x prime of t, r sub y prime of t. I didn't need to put vector indicators at the top of those. Those are functions. Okay, so r sub x prime and r sub y prime, and that gives us our velocity vector. So we can also call that v sub x of t and v sub y of t. So we have our velocity vector, which could also be modeled using parametric equations. And then the acceleration vector, which, by the way, the velocity vector, we would say v of t. Acceleration vector, a of t, would be the derivative of the velocity vector. And so that's going to be v sub x prime of t, v sub y prime of t, which we could also call a sub x of t, a sub y of t. Okay, so nothing really new there. We're just writing these things in vector form rather than working with position function, a velocity function, and an acceleration function. The only difference now is that we have a separate position function for x than we do for y, a separate velocity function for x than we do for y, and so on. Okay, we also talked about displacement and distance traveled earlier in the year. Displacement you can think of as net change. So the displacement on the interval from A to B would be the net change in position on the interval from A to B. And how did we get net change? How do you get net change in position? What kind of integral? What's that? What are we going to integrate if we want change in position? Yeah, you always integrate the function's derivative to find its net change. So this is the integral from A to B of the velocity. So our displacement vector is going to have the integral from A to B of the x component of velocity, and then the integral from A to B of the y component of velocity. Okay, so our displacement vector is going to give us a net change in position. And so we can integrate the x component and y component separately. So that means if we want a position vector and we know the velocity vector, position vector at time t, we would do the initial x plus net change in x, then we would do the initial y plus the net change in y. So that is r sub x of 0 plus the integral from 0 to t of v sub x of t dt. And then the initial y position plus the net change in y. And then distance traveled is going to be an integral from a to b of the magnitude of the velocity vector. And remember, to get the magnitude of the velocity vector, we use the Pythagorean theorem. So that's going to be the square root of the x component of velocity squared plus the y component of velocity squared with respect to t. Any questions so far? Anmol? Because when you do an integral, that just tells you how much something changed. If we want to know where we are now, if I say you moved 10 units to the right, do you know where you are? No, you have to know where you started. If I say you started at the point 2,6 and you moved 5 units to the right, now you know where you are because you take your initial position plus the change. Okay? You're welcome. Okay, so go ahead and use the relationship between position, velocity, and acceleration to write a velocity vector and an acceleration vector given the initial position vector up the top. Okay, so if we take the derivative of the position vector, we get the velocity vector is going to be 3t squared minus 4t and 2t over 3. And then if you take the derivative again, you get the acceleration vector, and that is 6t minus 4 2/3. Any questions on that example? Okay, go ahead and try the last problem, example 4. Given the velocity function, find the position at time 2 and the distance traveled on the interval from 0 to 2. Okay, to find the position at time 2, we're looking for the vector r of 2. We're going to do the initial position, the initial x plus the net change in x. So that will be the integral from 0 to 2 of t squared plus 1 dt. And then the y component is the initial y value plus the net change in y. And so when you evaluate both of those expressions, you get 12. And then for distance traveled, we're going to integrate from 0 to 2 the magnitude of the velocity vector. And that is the integral from 0 to 2 square root of t squared plus 1 squared plus 5 squared dt. And you'll want to evaluate that integral on your calculator and get 11.235. Okay. Questions on either of those? All right, so that is it for lesson 10.2.